Right. So right. Okay. So since Britton brought up Crackle, I thought I'd tell you about another thing we've been working on, which is called Crackle. Well, this is basically me working on it. So it's basically okay. So Britton just told you what Crackle is. I just wanted to make the point that the front end interface is in C. Okay, not the PyGrackle version, the main one that you embed into your simulation code. Under the hood, it's all a bunch of vectorized Fortran. So, yeah. Right. So yeah, this is, various levels that you can go to: fully equilibrium, non-equilibrium, primordial. You can add H2 chemistry, right? And even deuterium chemistry. Okay. Then a student of Britton's and mine, Ewan Jones, actually integrated Simba's dust production and destruction model into Grackle. Okay, so it's kind of level 2, but a different branch of it. And yeah, again, you just give it the properties and it gives you a bunch of nice things. Okay, so this is basically what Ewan did. So in Simba, we had dust production. We had H2, a model for H2. Actually from Robert Thompson again. But these things are not connected. Like this one was just sort of doing dust based on whatever conditions happen to be there, and same thing for the H2, right? In reality, of course, what happens is that the dust is catalyzed, or sorry, the H2 is catalyzed on dust. The dust, of course, is heated by the interstellar radiation field, which comes from the nearby star from it. There's this whole cycle of stuff, right? And so that's basically what Ewan did. So not only he added the molecular hydrogen, but he did it with, following all the reaction rates. We have the dust growth and destruction, but has now a dust temperature solver. So instead of having to assume a dust temperature, we now self-consistently calculate it. So then we can follow the H2 reaction rates, including this H2 plus grain, which is actually the dominant thing, right? So essentially it's a way of reforming H2. And then we have a multi-phase interstellar medium model. So for those of you familiar with something like Calibre, this is our version of that. Okay. So all of this is being self-calculated, or calculated self-consistently during the simulation run. And all this is embedded within Crackle now. Okay. But you just have to get Ewan's fork of it. So that's Ewan's fork, and you have to check it out. You have to check out Kiara. So basically, this now allows you to take Grackle and add a dust solver, right, in with it, right, and just kind of for free. Right now, it's tracking 11 elements. Now, the dust, of course, depletes differently on different elements. So now, into Grackle, we have to actually give it all the metallicities and the dust contents and take them out. So it's a little more I/O into Grackle. But again, it moves the metals around between metals and dust during the code. So you don't have to worry about that, assuming you're happy with things, including various processes. The dust has to be initially seeded in the main code. And you also have to provide an interstellar radiation field strength, which you can compute in some approximate way. Ideally, you would do the full radiative transfer, which Jen is going to be doing. But if you don't have that, because it's very, very expensive, you can make some decent approximations as Ewan did. Right now, it's only a single grain size, but this is almost trivial to extend. We just do it. This is the big problem. Okay, we put all this into the code, and it ground to a halt. Okay, just to kind of illustrate this, we put it into Swift. And so Ewan tried it in Gizmo. He had put it into the Simba Gizmo code. The Grackle kind of dominated the runtime. And with Swift, it's almost even worse. So yeah, this is just the cumulative time for simulation, and that's Grackle's time. So that's not good. So I was on sabbatical in Stellenbosch for about 5 months, and in between visiting wineries, which was the main purpose, I rewrote all of Grackle into C. And so basically, so that's what I'm calling Crackle. Okay, so. But it all has the same API, right? And the only thing you have to do is basically, instead of use Crackle equals 1, you set it to use Crackle equals 2, right? After you downloaded Crackle and sort of have these drop-in replacements. There's information on the website how to do it. I checked that it gives the same answer for a single step, but my sub-stepping is different, mostly because I don't quite understand how Crackle is doing it. It's a much sort of tidier code. It doesn't have these gazillion little Fortran loops, which I think also makes it a lot faster because essentially there's a lot less, just the way the data is structured now, I structure it in a way that has a lot less cache misses. I think that was the main problem, right? And I can also just optimize things a little bit in terms of the calculation. So you see now, basically Crackle is down here, right? So it's not great, but it's certainly a lot better now. The usual hydro and gravity are dominating the times.
Only you see to revise the first resolution part or all the function.
So it's rewrote everything that we needed for this, which is everything up to level 2 Crackle computations.
Okay.
I think it even has hooks for the deuterium, but we don't do anything with the deuterium. So in terms of anything extra, right? So
primary hydrogen part is also.
Sorry?
I mean the hydrochemistry.
Yeah. So hydrogen helium is all non-equilibrium. H2 is, it's exactly the model from Ewan, right? It's just implemented in C and optimized and is much faster. Okay. So that was basically it. So yeah, I think, it should work in principle for other levels and stuff. In fact, I know it does work for level 1 because we use it to test. I haven't checked level 0, but I'll use that. Probably look up tables, but we can do better. So essentially, but otherwise it's really just a drop-in addition to it. And so yeah, I think it's fun, and if anybody's interested in using it, just feel free or contact me. Yes, that's it.
Nice. Okay. So we've had so much fun.